Okay. Let's see here. All right. So, great job. Quiz number 1, done. Good job. So now that I've finished marking it, you'll be able to go in and review it so you can do it for ungraded practice. So same thing with the assignments. Once they've closed, you can go in and you can use them for ungraded practice so it doesn't affect your grade, obviously. Right, and so you can go in, there should be feedback. I don't really know what it looks like on your end, but I did write, if I changed your grade for whatever reason, I would write a little blurb, and especially for that, the written answer, then I gave you, some feedback there. So there's definitely gonna be at least one feedback box. So if you can't find that, hey, I entered this already, then let me know, but it will be there. Oh. I already did this. All right. So, good job on quiz number 1. Today we're going to start a section or a chapter called probability. That seems vague. Let me grab the textbook. Probability. I clearly did not do ballet growing up. It's good for the jokes. Okay. So chapter 3 is vaguely called probability. Now, probability is something that we're going to use throughout the rest of the term, but not in this sense. So here we have to introduce a lot of different calculations and a lot of different terminology, and kind of the good and also the bad part of it is that we don't really use it later on. It's another one of those things where we have to cover probability. We have to talk about things like probability notation. We have to talk about things like set notation, right? And so this is how we do that. But on the upside, it's not going to come back to haunt you really, right? It will be on quiz 2. There will be, I want to say, 1 question on the final exam, right? On this chapter. It's not a big player. So it's just something that we need to get through. And for that reason, I'm sticking very closely to the textbook. Okay. Very closely to the textbook. I will be grabbing kind of large chunks out of the. Okay, so that's annoying if you're writing hand notes, but you've been warned. So it might be helpful if you have done the pre-reading, right? We just did a quiz. How am I supposed to remember to pre-read too? Next time. Can't win them all. All right, so this week, we're gonna do 3.1 and 3.2, kind of quick pace. 3.3, 3.4, 3.5. Those aren't really important for us later on, so we're gonna do them very quickly. All in one day is what I'm hoping. Which seems like a lot, but that translates to questions as well, right? They're not really going to come up. But again, just so we can say that we did it. We were there. All right. So let's go to last class. I know you had a quiz, but before that, we worked through a question like this one from your assignment, but then it also appeared on the quiz. I know what you're thinking, Emily, that's so fair. I know it is. And what we said, we kind of gave a little preview, a sneak preview, and we said, okay, well, here we're talking about percentages. But then we also said, okay, well, percentages are from proportions, and then proportions are probabilities. And so we've already kind of found probabilities, we just didn't call them that. Okay. So I'm going to snag this question here. Why not? Copy. So from last day, September 22nd, I know it's not technically last day. We used the contingency table to find percentages. We used a contingency table to find percentages. All right, and let's see here, make it a little bit bigger. So we looked at a question like this, and here the question was about the percent, right? What percent? So that tells you how to answer the question. But then let's use a perkier color, right? We established that, okay, it's good to keep track of, okay, these 3 P's, they all mean the same thing, right? And so we said that, or we noted that and I call them the 3 P's, right, are interchangeable. Yeah. Which means that a proportion is a probability, which is roughly a percentage. Right. We had to multiply by 100, but basically. Right. And so that's where these 3 P's come from: proportion, probability, and percentage. So what we could do is we could rewrite this question, and it could ask, what is the probability of randomly selecting a Tampa, Florida voter who identifies as conservative? Right. That's the exact same question, just in terms of a probability instead of a percent. But if we introduce that right away, that's really scary, right? So now we've seen it, we can kind of handle that. Okay, so we can reword the above question as, how did I say it? What is the probability? What is the probability and here's where we introduce a new thought of randomly selecting, right? And so, but to be proper, we have to say that randomly selecting a Tampa, Florida voter. It's tempting to leave that out, right? But that defines who we're talking about, right? They have to live in Tampa, Florida, and they have to be a voter, which excludes part of the population of Tampa, Florida, right? So we have to be really specific. And how did it? Who identifies as a conservative? Let's say that. Who identifies as a conservative? That's the same question. So then the answer, a proportion is a probability, right? Or that means a probability is a proportion. So then the answer is going to be 0.3952, let's say. So the answer here is approximately, because I'm going to round, 0.3952. Proportions have to be between 0 and 1, right? And same thing with probabilities. And so a probability, let's just have some quick rules here. Rules for probabilities, which also apply to proportions, right? For probabilities / proportions, number one rule is going to be that a probability has to be between 0 and 1, right? And so I don't know, I think a lot of you might know Stephen Brown. We share an office, and there's other people in there too, but I'd say we're like the main two. No. And this morning he asked me, what's the probability of your students liking probability? And I said 0. So I'm sorry. And he said, at least it's not negative, because it can't be negative, right? So it's pretty good. So a probability must be between 0 and 1. And 1. It's time for me to have that panicky moment of, did I start recording? Phew, okay, I did. One of these days, I'm gonna find that I didn't, but not yet. The second rule for probabilities, and we kind of understand this already intuitively, is that the total probability, if you're considering all possible outcomes, then the total probability has to be 1, right? And so the total probability of all possible outcomes must add to 1. Oops. Yeah. Right. These are just some probability, but also proportion rules, right? But definitely for probability. Okay. Good. So in this section, there are a lot of things that we know already, or kind of intuitively know, right? But what we're going to do in this section is we're going to assign notation and terminology to these things that we already pretty well understand. For example, if I ask you, okay, I'm about to flip this coin, right? What's the probability of heads? You're all going to say 0.25, no, 0.5, right? 50-50 split, right? 0.5 and 0.5. What did your brain do? Your brain looked at, okay, well, there's 2 possible outcomes, right? And so the total probability must be 1. 1 divided by 2 is 1/2. So your brain already does it, but now we have to attach that to math, and that's the hard part, right? If you roll a die, a 6-sided die, right? The probability of rolling a 2, 1 in 6. What did your brain do? It took the total probability, okay, 1 divided by 6 possible outcomes, 1 in 6. There's an added thing that makes it harder to wrap your head around, is every time that I roll this die, okay, I have a 1 in 6 chance of it being a 2, for example, right? Or any one of those numbers. Okay. But we rely on something called the law of large numbers that says, okay, if I roll a die 6 times, for example, I don't expect a 1 and a 2 and a 3 and a 4 and a 5 and a 6, right? They're not going to happen like that. It's not unless I roll them an infinite number of times, kind of simulate it, right? That's when I get to the 1 in 6, but that's how it works out. So that's why we're able to do that and start a fresh page here, section 3.1, and that's what we're going to talk about. Defining probability. So from the textbook, I'm going to steal a little ditty here. And I encourage you, there's lots and lots of examples in the textbook as well with videos in case you haven't checked it out. So they do have these videos and slides. There's tons of resources here, almost too much, right? Just give me what I need, nothing that I don't. Not quite how it works, right? Okay, so here, I want to talk about this. Terminology begins. So when I flip a coin or when I roll a die, those things, we call those a random process. Okay, a random process generates some set of possible outcomes. Okay, and so the outcomes are these things. So if I roll a die, I can get a 1, a 2, a 3, a 4, a 5, or a 6, right? And if I only roll it once, only one of those can happen, right? Same thing, if I flip a coin, I can get a heads or a tails, and that's it, right? So there are only 2 possible outcomes. So first, these are your outcomes. Whereas the random process that generates these outcomes are the action of generating some outcome. We're going to focus on the term outcome. So the random process generates an outcome. That's all you need to know. But in terms of kind of grasping the term outcome, that's going to be important. Right? So, okay. What we said was the probability of an outcome. Here I go again. I know, so rude. But it's all here, right? Just to keep it nice and concise. I'm trying so hard to follow the textbook almost exactly, but I have my own spin on things. So the probability of an outcome, so this is the definition of probability. The probability of an outcome is the proportion of times the outcome would occur if we observed the random process an infinite number of times, right? And so that's where probability comes from. And I know, at least for me, when I was learning this stuff, I got hung up on this, observe the random process an infinite number of times. Well, I haven't done that, right? I'm just trying to figure out the probability of rolling a 2, right? But because of how probabilities work and the law of large numbers, which I won't put in our notes, but here they do talk about the law of large numbers. It says that, okay, flipping a coin, if you flip a coin 10 times, for example, we understand that it's not going to be 5 heads and 5 tails exactly, right? There's probably 4 and 6 or some combination, right? There's this variability that we have to deal with, right? But if I flip it or if I roll a die a large enough number of times, then what happens is the proportions start to stabilize around that overall 1 in 6 or 1 in 2 probability, right? And so that's why we're able to use it. That's kind of background knowledge that we don't need to pay attention to so much, right? It's the definition of probability, but for us, right? We find probabilities. We can find probabilities by dividing the total probability, which is 1, dividing the total probability which is 1, right, by the number of outcomes, right, by the total number of possible outcomes. So that's how we're going to find probabilities, right? We don't have to do any simulations or things like that. This is, of course, assuming that the probabilities are split evenly. If they're not, I would have to give them to you, right? But this is where we're starting, where things are just split evenly. Okay. So for example, if I think about rolling a die here, we have 6 possible outcomes. Which means that each has a probability of 1 in 6 of happening. Which means each outcome has a probability of 1 in 6. And maybe I can sneak that on the same line here. Notice that I keep the exact value, right? 1 in 6. You could convert it to decimals, but then you're dealing with rounding and stuff like that. So I just like to keep it as the exact value often. Okay. What we're going to find is we're going to add these and subtract these. And so that's going to be easier if we just have the fractions. Adding and subtracting fractions. Emily, don't you remember you need to have the same base? I do remember that. But they'll always have the same base, so it's not an issue. I know.
What does P with little hat mean?
Oh, busted. Busted I am. P hat is the sample proportion. I was avoiding it. Oh. We're going to get to the sample proportion, but for now, right, I'll say it here because it's a good question. P hat is the sample proportion. And just like when we talked about the sample mean, well, then we know there's population mean. And so usually I use P, which goes against our Greek letters. You could use pi, which is the population proportion. So we'll get there. Right. I'll say from the law of large numbers blurb, save for chapter 4. So soon, but not yet. Okay. So when we have a probability, then, and proportions are probabilities, sort of in this sense, but let's parking lot that. So if I have a probability, then instead of writing out the probability of rolling a 1 equals 1 in 6, right? That's really annoying to write. The probability of rolling a 2 is 1 in 6. We use shorthand, so probability notation. We often use probability notation. As shorthand. So it's going to be useful if you're able to read these as well. The probability of 2 is how you would read that, right? But what it means is the probability of rolling a 2, and then it's assumed that you understand that whatever you're talking about, right, the process that you're talking about should be obvious, right? When rolling a 6-sided die, for example, right? So here, you're going to read this as the probability of 2, which really means the probability of rolling a 2 when rolling a 6-sided die, or I should say observing a 2. The probability of observing a 2 when rolling a 6-sided die. Is 1 in 6. So usually the outcome, right, we can use some sort of shorthand for the outcome. Okay. So if I write P of H, right, then, well, what's the most logical choice for H? It's heads. So that implies that the process that I'm talking about is flipping a coin. And so then it's going to be 1/2. Even when it's not obvious from the question, you can define this, whatever the shorthand is, right, up above if you're going to use it a lot. And I'll show you an example. So, all right. Rolling a 2, flipping a head, right, that kind of thing. That's all fine. Pretty reasonable so far, probably. What if I'm interested in a set of outcomes, right? So rolling a 2 or a 5. So I don't care if which one happens, as long as one of those happens, then I win. Probably money, I don't know. That's usually what we use this stuff for, gambling. Well, it's the only thing that kind of gets us going. So win that money. All right, so what if we're interested in a set of outcomes? What if we are interested in a set of outcomes? Okay. For example, rolling a 2 or a 5. Rolling a 2 or 5. How would I denote that? Well, I'm going to have to use set notation, right? Because it's a set of outcomes. Set notation uses curly brackets and the entries separated by commas. Okay, so this is a set, and this here is set notation. And usually my left curly bracket looks so good, and then my right one, not so much. Takes practice. And I don't use a ton of set notation anymore. So who needs it except for probability and math, upper level math? Okay, so here we're saying, all right, now I'm interested in this set of outcomes, 2 or 5, right? So when we have a set of outcomes, we call that an event. And the textbook kind of confusingly uses outcome as a term for an event as well. So if you want to, you can just call them all outcomes, whether it's a singular outcome or a set of outcomes, right? They just generically call it an outcome. But in case you're interested and you prefer to call them events and differentiate between the two, that's what they're called. So we call a set of outcomes an event. Okay. And we denote an event using uppercase letters. We denote an event using uppercase letters. So for example, A can denote the set of 2 or 5. A is the set of 2 or 5. So this happened if I roll a 2 or if I roll a 5. Okay. And here, the textbook uses outcome to kind of talk about a singular or a set of outcomes. Uses outcome to refer to a singular outcome as well as a set of outcomes. Oops. Just as a note, that can be confusing. Yeah. So a set of outcomes, okay, that's useful, right? What if we use the set of all possible outcomes? That's a special set called the sample space. Well, the sample space which we denote. So again, it's a set, so we use a capital letter and we use capital S to denote the sample space. And the sample space is the set of all possible outcomes. So in the very beginning, when we listed the random process with the list of possible outcomes, really what I was giving was the sample space, or what they were giving was the sample spaces, right? And so now we can wrap them up in curly brackets, and that's all there is to it. So if you're rolling a die, the sample space S, the possible outcomes are 1, 2, 3, 4, 5, and 6. Okay. If I roll a die only one time, right? Only one of these things can happen, right? We understand that, right? And so even if I have events, as long as only one of them can happen, that's a special case where we call them, we say they're disjoint. Okay? And so outcomes themselves are often disjoint, not always, but often. And events can be disjoint as well. So if we roll a die once, right? So only one time. Maybe I'll emphasize that, only one time. We only observe one outcome, right? We just don't know which one. We will only observe one outcome. I guess we should apply terminology that we just introduced, right? One outcome from the sample space. Oops. So here, when only one outcome can happen, right, we say that these outcomes are disjoint. And only one outcome can happen. I'll say at a time. We call them disjoint. Or mutually exclusive. Glad I wrote a note here. Or mutually exclusive. We use those terms interchangeably, disjoint, mutually exclusive. I usually use the term disjoint, right? But mutually exclusive is fine as well. So events, right? Events are sets of outcomes, and they can also be disjoint as long as there's no overlap. Well, there are cases where there is overlap. That's very common, right? But let's start by talking about the special case where there's no overlap, right? But I'll show you what it looks like. So events can also be disjoint as long as there is no overlap. As long as there is no overlap. For example, if the set A is 2 or 5, as long as B doesn't have a 2 or a 5 in it, because then there would be overlap in those two events, right? Then they're disjoint. So then I could have things like 1, 4, or 6. Could be event B. Right? There's no overlap here, so these are disjoint. Whereas if A again is 2 or 5, but now B is the even numbers 2, 4, 6. Right? If 2 happens, right? So if I roll a 2, then both event A and B have happened, right? So then they're not disjoint. And maybe I'll put this down on a new page here. So I do want to talk about here. If I roll a 2, both events A and B have happened. Right, so there's overlap between the two, which means that they are not disjoint. Now, confusing, because wouldn't I call them joint? I guess I should, but I don't. Just call them not disjoint. I don't know why, but for some reason, we just don't do that. It's weird. So therefore, oops. Can't remember if I've asked you guys if you're okay with the shorthand for therefore. 3. I've asked, or you're okay with it. Okay. That means I probably should have asked my previous class. I've asked you guys twice. So therefore, they're not, these two events are not disjoint.
When you say event,
Mm-hmm.
that's the outcome of a roll of a dice, any of the 6 possibilities.
So I use the terminology event for the set of outcomes.
The set of outcomes.
Yeah.
Okay.
But if so A is the event. It is going to happen if I roll a 2 or if I roll a 5. And B is the event, which means that I either roll a 2, a 4, or a 6. Not sold, huh?
My brain hasn't pieced it together yet.
It's okay. We're going to do some examples. In fact, let's figure out the probability of A, right? If I asked you, if A is the set 2 or 5, right? Maybe I should say it's a little example. What is the probability of A? So we can use probability notation. The probability of A, well, I already heard 2 and 6, so I know you guys are okay with that, right? And again, it's one of those things that, okay, we've got a pretty good handle on this. It's when we attach notation to it, that's the hard part, right? And so, or not the hard part, but gets tricky or sticky rather. So the probability of A, well, is either when I roll a 2 or when I roll a 5. And so, well, that's the probability of a 2 plus the probability of a 5. Because there's no overlap, right? That's why I can go ahead and do that, right? I'll introduce what happens if there is overlap. So if they're not disjoint, we'll be able to deal with that. But this is a good place to kind of start our journey intuitively. Okay, so here, right, we take the sum of the probabilities of each of the outcomes that are in A, right? And so here we get 1 in 6 and 1 in 6. Right? They're all going to have a probability of 1 in 6. And, right, common denominator, so I'm allowed to add these. So then I get 2 and 6. Like I said, I usually just leave it as an exact number. So let's bring in the definition that we just developed. We got there on our own. Pretty impressive, right? It's called the addition rule of disjoint outcomes. So it's a special case. And it says that if A1 and A2, I use A and B, but that's fine, they're the same, represent 2 disjoint outcomes. So that's a key part of this. Then the probability that one of them occurs is given by the probability of A1 or A2, which is the probability of A1 plus the probability of A2, right? So here, A was denoting 2 or 5, right? So now we can translate that to the probability of A or B. But because if they're disjoint, then I'm allowed to just add up the probabilities. So here just to clarify, outcomes, you can replace that with events if you prefer. So, or events. I appreciate what they're trying to do. They're trying to minimize the terminology, but also it gets kind of confusing. Right? So here, what I want you to do is when you think of the word or when you see the word or, you're going to think addition. Because on the flip side of that, and we won't get there quite today, but tomorrow, or I guess Thursday, no, tomorrow, our secret class tomorrow, you guys didn't know? Oh boy, no, Thursday. Then the opposite of that would be and, which is going to be multiplication. So there are two things, but it's nice to get started with the or and think, okay, then I'm going to attach addition to that. Okay, so when you see the word or, it means that either outcome can happen. Okay. It's like the slowest door ever. Either outcome can happen. All right. And like I said, when we see the word or, right, should make you think, okay, that's addition. Okay. The word or should make you think of addition. Dreaming of addition. But just to see where this is going, right, for next day, the word and is going to mean multiplication. But for now, right, or is going to be addition, or in general, it's going to be addition, which here, right, the probability of A1 or A2 is the probability of A1 plus the probability of A2. Right? If you have many disjoint outcomes, as long as they're disjoint or disjoint events, as long as they're disjoint, you can find the probability of any one of those happening by adding up the probabilities. Okay? So, like we said here, the probability of A, well, A was really a placeholder for 2 or 5. A is 2 or 5. Right. And then it maps to the exact same formula. Yeah. Not all outcomes are disjoint, right? So what happens if they're not disjoint? Then we know we can't use this formula because it's only for disjoint outcomes. Okay, surely there's a way to deal with that. Oh, there is. What if we have non-disjoint outcomes? Or events. Are they moving stuff out there or what? So for example, my go-to, if A is 2 or 5, and let's use that B is the set of the evens, so it's going to be 2, 4, or 6. We already saw that 2 is in both of these, right? And so here there's some overlap, which means they're not disjoint. So if A is the set of 2 or 5, and B is the set of 2, 4, or 6, right? What if I wanted the probability of A or B? Oh boy, right? Then it can be a 2 or a 5 or a 2, but I've already done that one, so let's ignore that one, or a 4 or a 6, right? So here, what if we wanted to find the probability of A or B? Okay. The probability of A or B, right? Knowing that they're not disjoint, right, is going to be the probability. So now it's usually easiest if I can just rewrite these in terms of the actual values to see that there's overlap. So A is going to be 2 or 5. And then or B, so then I can just link those up and keep piling stuff on, right? 2 or 5 or 2, but I've already done that one. Good, but I'll write it down just in case, or 4 or 6. Already counted this one here. So what happens, and now it's time to introduce the real formula. Come back to that. It's called the general addition rule. Because we see that there's going to be trouble with this overlap, right? So we need to deal with that. And so the general addition rule says that if A and B are any 2 events, disjoint or not, well, why did we need that special case then? We didn't, but we're building to it. Then the probability that at least one of them will occur is the probability of A or B starts off the same, right? So, or I think addition. So the probability of A plus the probability of B, but then I have to subtract this overlap, right? And so where the probability of A and B is the probability that both events occur. Right, and so here, this is the overlap. Or it's the probability that both of those things occur. I never want to say it normally. Okay, so the overlap, let's map back to here, and then we'll tackle, okay, so we can use this one even if they're disjoint. Okay, fine, let's tackle that first. It's an easy win. What's the probability of A and B if A and B are disjoint? That means that there's no overlap. So the probability of them happening together is 0, right? And so it's just a special case where the overlap, well, there's nothing. So the probability of that is 0. So technically you're just subtracting 0, right? And so when A and B are disjoint, the probability of A and B is 0, since they can never happen at the same time. Since they can never happen at the same time. So now, if I map this back to the probability of A or B in terms of up here, then I have the probability of, well, I'll start again, A plus the probability of B minus the probability of A and B. And of course, I'll give you these formulas, but I think they are pretty intuitive, but I know that's not the case when you're first learning this stuff. So on the quiz, you'll have the formulas. For assignments, just make sure you have them handy. Okay, so this translates to the probability of 2 or 5 plus the probability of 2 or 4 or 6 minus the probability of 2, right? That's when A and B happen, which puts me at probability of 2 or 5. Well, that's 2 and 6. The probability of 3 of the 6 possible outcomes, I'm gonna keep it as 3 and 6. It's tempting to do 1/2, right? But then all of a sudden I can't add these because they don't have a common denominator. Minus 1 and 6. 2 plus 3 minus 1 puts me at 4 over 6. Which is also, of course, the number of outcomes, unique outcomes out of 6 that we're looking at, right? 2, 5, 4, 6. Correct. So a common thing that we use is a deck of cards. And if you've done any combinatorics in high school or anything like that, probably remember this dang deck of cards. I've had students tell me, well, I don't know what a deck of cards looks like. So let's go through some basics. I had one student tell me that they should not have to do these questions because they don't know what a deck of cards looks like. So here I'm trying to get around that. It's not a very reasonable excuse. So here's a deck of cards. I always struggle because I know there's 4 suits, but the little clovers and these little guys, I can never remember, but I know from this morning what they are. So let's establish this first. Okay. There are 4 suits. Okay. And the suits are appearing in this order: clubs, then it's diamonds, hearts, and spades. Yes.
I have a question with the general formula, the overlap.
Yeah.
You have A and B there. If
Yeah.
there's 2 overlaps, would it be like, for example, 2 times 4 because of the and there, or is the and just a general language?
The and is just general language. Yeah. Confusing though, because I just said multiplication and it will be, just not yet.
Okay.
So for now, it's just the overlap, general
So if
language.
there was another outcome, it would be 2 to 6. Minus 2 to 6, like that is.
Yeah, so if this list was 2, 4, or 5, then the subtraction would be 2 or 5.
2 to 6.
Yeah. Exactly. Good. Okay, so there are 4 suits. There are, oh, and I cut off the figure, which explains that there are 52 cards in a deck. What are some other things? There are 13 cards in each suit, which we can see here. If we counted, there's 13. So here, 13 cards in each suit. So already we can ask questions like, what's the probability of drawing a diamond card? Well, 13 and 52, right? There are things, what are some other things we could talk about? These are special cards. They're called face cards. So there are 3 face cards.
Isn't ace a face card too?
Usually ace is not, it's not counted as a face card. I don't know why it's over here. Usually it's over on this side, but it depends on what game you're playing, right? Aces are high, aces are low, but there's 3. So the face cards are the ones with the actual face on them. So there are 3 face cards in each suit, which means that there are 12 face cards total. So what's the probability of drawing a face card then? Must be 12 and 52, right? You're randomly drawing. Okay. So here's where we start denoting events by capital letters. And so if I'm nice and I want to cover all my bases, then I might say something like let H be drawing a heart. And F be drawing a face card. Oops. Start over. So then we already established that the probability of a heart must be 13 and 52. And the probability of a face card we just established was 12 and 52. What's this entire block called? That's our sample space, right? These are all the possible cards that I could draw, right? And so lots and lots of questions we could come up with here, things that we're interested in, right? But I like to stick to the basics, like these things that we've talked about. What if, and what's nice when we have the entire sample space laid out, we can actually kind of put together the probabilities, right? The probability of a heart, well, you could count, even if you just had this image, you could count how many cards there are and how many are hearts, and then you would get to the 13 out of 52. So it's a nice way to start. Same thing with the face cards. What if I wanted to find the probability of drawing a heart or a face card? So now I'm opening myself up to either situation, but notice, of course, there are going to be 3 heart face cards, right? So if I look at all the hearts, I see that there's 13 hearts, and then I see that there are 12 face cards. But notice that I've counted these heart face cards, heart and face cards twice. So that means that I need to subtract that out. Let's see. So if I do the probability, I'm dealing with a page break that's going to mess stuff up here. Put on a fresh page. The probability of a heart or a face card. If I map it to the general addition rule, right, the probability of a heart or a face card is going to be the probability of a heart plus the probability of face card minus the probability of a heart and a face card. Plus the probability of F minus the probability of H and F. And I want to highlight that minus because sometimes we get to thinking plus and then we accidentally add it. But then just remember, you have to subtract that overlap so you're not counting it twice. So we found these probabilities. And I guess we even saw that the probability of drawing a heart and a face card, well, that's these three here, 3 out of 52 cards satisfy that criteria. So then put it here, the probability of H and F is 3 out of 52 cards. So I have these probabilities here. Now I can plunk them into my formula and be on my way. 13 over 52 plus 12 over 52 minus that overlap of 3 over 52. Nice. I'll just show that I'm allowed to combine the numerators because I have a common denominator. Oh, stop it with that, Emily. We don't want it. 22 over 52, I'll keep it on the same line. Otherwise, it's like rows upon rows, math. This fraction is what we call the exact probability, or the exact number. Some questions will ask for the exact probability, so then you'd need to maintain those fractions. Or if you wanted to approximate it, because our brains don't really do a good job of, so if a friend asked you, hey, what's the probability of me drawing a head or a face card, or sorry, a head or a face, those are the same, heart or a face card, right? And you told them 22 out of 52, to get out of here with that, you'd say, okay, fine, 0.42308. Right, that's the approximate probability. Good. So in terms of organizing information from these questions, usually a Venn diagram is going to be helpful, or it can be helpful. Now, Venn diagrams are not something that you need to use. You don't need to use them, but they do make life a little easier. So I just want to show you how they're set up to help organize information. From a question. A Venn diagram can be helpful. A Venn diagram can be helpful. Probably seen a Venn diagram before. They're usually they make pretty good jokes, right? You've got event A and event B, and then there's some overlap, and usually the overlap is the funny part, right? That's generic, I know. A Venn diagram looks like this. You start off and you make a rectangle, and that's to denote your entire sample space. So this is the sample space. Then, usually, I have some event A and some event B, where this overlap here is when A and B are happening. Okay. So how's this useful? Well, often, as long as we're able to attach values to these spaces, then we can just look at these spaces and figure out which ones satisfy the criteria of the question. Okay? And so here, if I have this area, which does not include the overlap here, that's when only A happens and not B, right? A happens regardless. It happens inside the whole A circle, right? So it's the orange area plus the pink area. Same thing with B. If I'm interested in, okay, what about when only B happens, only B, not A, then I have to kind of carve out this midsection here, this overlap. Everything outside the circles, that's everything that's not in A and not in B, right? We're gonna talk about complements next day. Complements. No, the complement of an event, fun to say, fun to do, is just it not happening. So when A doesn't happen, that's everything outside of A, right? And so on and so forth. So there's lots of questions that we can answer by just using this Venn diagram. But of course, it all hinges on having the right numbers here in these areas. Okay? So when you set up a Venn diagram, when setting up a Venn diagram, oops, I don't know why I did an S there. Start by filling in the value with the most overlap, right? So you always start in the very, very middle. We can even do 3 events, but all right, we'll get there once we have the basics here. So when you're setting up a Venn diagram, start by adding the value with the most overlap, right? So start by filling in the value of the area with the most overlap. All right, okay, we can do that. Let's set one up for the previous example. How did I have it? Heart, then why do I want to say head? It's from flipping coins. Heart or face. So then here, there were 3 cards that were both heart and face cards, right? I had a total of 13 hearts, right? But I've already taken 3 of those, right? And so here I have 13 minus 3 equals 10. And this is the count for what I like to call this half moon area. So often if you're sending me questions about these, then I would talk about the half moon, right? The H half moon. And so I do want to make a note of that here, right? I call this the half moon area. I don't know how else to describe it. Kind of only H, huh? The Pac-Man. But what does that make this one? I call this one the half moon as well. The other Pac-Man. So then here, if I'm talking about only F, well, there were 12 face cards, but 3 of them are already accounted for here in this overlap, right? So then I have 12 minus 3 equals 9 cards that are only face cards. Okay. And finally, knowing that the total sample space is 52, right? So maybe out here, I'll say 52, then I can figure out how many are not in H or F, right? By taking 52, I'm almost there, right? So then this area would have 52 minus 10 minus 3 minus 9, right? I just take away all those puzzle pieces. And 30, so 30. There I have all my components. Okay. So I can answer questions like, what's the probability of only drawing a heart that's not a face card, right? 10 in 52. What's the probability of drawing a card that's not a heart nor a face card? That's going to be 30 in 52, right? So we can use all these puzzle pieces to piece together what we need. So we'll pick up there next day. If you have any questions, let me know. Otherwise, I'll see you Thursday.